In any case, besides saying happy birthday, I want to repeat what I said yesterday. Chris was a great student, is a great mathematician, and the best thing of all, he's my friend. So I really am thrilled that we are friends. Now, those are facts. I want to begin with a little bowl. This is, there's a farmer in Spain, Farmer Picasso, and this was a bull he made in 1945. It was a big year for making bulls. And he was a very sort of artistic guy, and this is his bull, Pablo. And he wanted to try to explain abstraction. And so what he did, you can check museums, any place of this, these are facts. What he did was, in just a series of half dozen, maybe 10 sketches, and each sketch N, looked such and such, and then sketch N plus one of that looked a little more abstract. And so in about 10 sketches, he got down to this. And he said, this is abstraction, guys. And so this was abstract art. And he had a following, of course. And at this point, when I speak in museums about art, I put a wordy slide like this here. I've never spoken in a museum about art. But along the way with those sketches is this one here. And so this is my interpretation of Picasso's spectral synthesis of Pablo. And what he did was, he didn't say this, he was doing abstraction, but this is the intersection with synthesis. What he said was, let's build a bull or other things from building objects that we decide on in advance. For example, we talked about Lego earlier today. I didn't, but that was a very good topic. And these aren't exactly triangles, but you can think of this as being a bunch of rectangles and triangles. And this is the road to that little 3 or 4 lines from Pablo. And this is, in some sense, a spectral synthesis of the bull. We have built the bull from triangles. And that's what spectral synthesis is all about. We start off with building blocks, like bricks if you want to build a house or something else, or Lego, or triangles. And you want to have a way of building it, a topology or a really good artist. You've got your building blocks, which we're going to call its spectrum. And then the synthesis is putting together that object, the bull in the original case, in terms of those building blocks. So I'm not going, that's the end of the bull. Thank you. So I want to say the spectral synthesis really is synthesis, reconstructing complicated objects in terms of natural spectral building blocks. For example, I want to take L infinity. I'm taking it on the real line, but we're going to get more general. But the real, we can envisage that to some extent. And I like L infinity. It's not as deodorized as L2, where everything's perfect. It's not as canonical as L1. You got to start off integration theory. But it's a little dirty. There are noises in there. So let's start off with a serious space like L infinity. And now we're going to say that the spectrum of an element of L infinity is the support of this distribution T. And so all I'm taking is the distribution T also on the real line, which is the dual group of that R, where T hat is equal to F. So that's a very reasonable definition of a spectrum of a given function F in L infinity. It's not the only one, but it's the one we're going to think about. And This is very convenient for me because I don't want to talk about spectral analysis today. And so I'm just going to say we have a spectral analysis of L infinity. It's a fait accompli. We've done it all only in the sense that I'm given an element of L infinity, which is not the zero element. I'm looking at the support of the distribution it comes from. It's got stuff in it. It's not empty. And so I'm going to say we have spectral analysis because I want to talk about synthesis. And so now let's move to this fourth bullet. And a spectral synthesis of F is a Fourier reconstruction of F from the support of T. That is to say, and we can think in terms of Fourier series, if I look at the elements of the support, those harmonics, the things that you make exponentials with, if you're talking about a Fourier series or Fourier transform, you've got your function and then you've got those exponentials. Well, instead of something like L2 convergence or whatever, I want to use the weak star convergence on L infinity and L1. Why would I want to do that? Not to show off, you all know this stuff better than I, but the advantage of using the weak star topology is I get a big space in the sense that I use the weak star topology to reconstruct. In fact, since the weak star topology is such a weak topology, there's more of a chance of synthesizing a large space of L infinity. If I want to do synthesis, I'd really like to synthesize everything. For example, when the Lucene conjecture came down the pike, people wanted to know if every L2 function, converged, and it did. Thank God for Collison, who also came up earlier today. And so I would like to get a weak topology so that I can get synthesis for as large a subspace of L infinity as possible, the analog being something like L2 for Lucene. The flip side of that, let's go to this fourth point here. We could get I'm still on the real line, I'm still thinking of bounded functions, but we could get a smaller synthesizable space. A smaller subspace of L infinity is the bounded continuous functions on R. And a smaller space than that are the almost periodic functions on R. I could define them, but I'm not going to because of the strict time limits that have been imposed on me. In any case, I have a smaller synthesizable space, and I'll invoke a stronger topology. For example, in the case of the almost periodic functions, I take that smaller space and I'll use, why not, the L infinity norm. And we can play the game of synthesis for that. It's a fun game. You can play it in all sorts of environments. Now, I brought up the almost periodic functions for several reasons. So I'm going to look down here at the bottom. My last topic was almost periodic functions. Well, Harold Bohr, the second brother, that's a tough place to be. After almost periodic functions was so important in astronomy, actually. Its original applications were in astronomy. Then he got really involved in analytic number theory and in Dirichlet series. And I mention that because we're going to talk about that at the end. Now, that is, I know I'm insulting my non-US friends here, but I'm going to call that a soccer ball. I know it's a football, but I don't want to offend any real Americans by calling it a football. So what you see when you look at the soccer ball, you see a dodecahedron on steroids. You've got this dodecahedron, the black guys there, and you've patched together a bunch of hexagons there. So it's more like a ball. And I haven't told you what a set of spectral synthesis is yet, but I want to give you some advanced advertising. I used to be able to prove that that was a set of spectral synthesis. If you really made a genuine basketball out of it, that's not a set of spectral synthesis. So the subject has subtleties, really deep subtleties. Okay, let's establish some simple notation. So let's just look at the first two lines there. I'm going to let G be a non-compact, locally compact abelian group. If you don't know what that is, it doesn't matter. Take the real line, take RD, just make sure G is not compact. Now, once I have L1 of G, I can have the Fourier transform that we all know, and I'm going to call the space of Fourier transforms A of gamma. And gamma is the dual group of G. And now I have the natural topology in L1 of G. I put the topology inherited from L1 of G on A. That is to say, if phi belongs to A of gamma, and phi is the Fourier transform of F, then the A norm of phi is just going to be L1 norm of F. Then I look at the duals of that first line, and we all know from real analysis that the dual of L1 is L infinity, and we're going to call the dual of A gamma, why not, A prime of gamma, very original. And let's skip ahead to here. A of gamma is a commutative Banach algebra of absolutely convergent Fourier transforms under pointwise multiplication and multiplicative unit 1 when gamma is compact. If we look at A prime of gamma, what's in there? And think RD, but you can think this other generality if you want to. The bounded Radon measures are contained in there. That's a good thing because measures play a big role, well, all over the place, but in this subject in particular. And A prime of gamma, which I'm calling the dual space of A of gamma, is the commutative Banach algebras. We're going to call them pseudo-measures. They're a subset of the space of distributions. They're Schwartz distributions in the sense we can take their Fourier transform. Convolution is naturally defined in it, and it's got the multiplicative unit delta. Okay, so the major thing from this slide, remember, are the first two lines, just to go back and forth. Because right until now, spectral synthesis, the only thing I said about it, besides the corny joke about bulls, the only thing I said about it is that it's really writing down a Fourier expansion of something. Given that F in L infinity, writing down its Fourier expansion. But the subject is much more subtle than that. Now, it deals with the ideal structure of L1 of G or A of gamma in the following way. Let psi be an A of R, and let's look at the zero set of psi's. The set of elements gamma in R, and that R can, in R, and for which psi of gamma is equal to 0. Okay, that's the zero set. And so the zero set of a subset of A of R is exactly how we define it. The zero set of X is a set of gammas in R, such that for every element in X, psi of gamma is equal to 0. Now, let's let E be a closed subset of the real line. Then we're going to define K of E to be all the elements of A of R where psi is equal to 0 on E. So I've got the real line here. Unfortunately, by using the real line, since they're self-dual groups, you miss the point that it's the dual. But I'm looking at the element psi over here on the dual group of the R over here. And in any case, that's, I'd say, obviously an ideal in the algebra A of R. And it's a closed ideal. I mean, I multiply any element of A times an element of K of E. There it is, whammo, back in K of E, right? I want to look at another ideal. Let's call it J of E. And J of E is going to be the elements of A, so that E intersection the support of psi is the empty set. Okay, so here's where F is defined in L1. I'm over here where the Fourier transform is defined. I'm going to take a set E in here, closed set, and now I'm going to look at all the elements in A which vanish from the neighborhood of E. Well, that's also an ideal. So I close that baby up, and I've got another closed ideal. J of E closure is obviously contained in there just by the way I define things. And this is where some mathematics is involved, which I'm not going to talk about. This talk is almost completely mathematical free, but it's not actually. But by a generalization of Wiener's Tauberian theorem, which I promised someone I would mention today, we have the J of E closure is the smallest closed ideal, and K of E is the largest closed ideal, which have E as the zero set of those two ideals. Okay, this ab initio, looking at it at first blush, doesn't have anything to do with that Fourier expansion I gave, but it has everything to do with it. So we're going to define a set of spectral synthesis. So it's defined in the dual group. A closed set E is a set of spectral synthesis if these two ideals are the same. And there you go. That's a definition. Set of spectral synthesis, and several slides earlier, a Fourier analysis of F in L infinity. And it's all the same baby. And one of the reasons it's the same guy and whatever is because of the Hilbert-Nullstellensatz. And so this subject has very, to me, fascinating origins, because it really began with Emmy Noether and Hilbert and the Nullstellensatz and the ideal structure of, well, polynomial algebras. And then Berling and Wiener came along last century and thought about things analytically, and everything's sort of the same. So this is a busy slide, and it's a late day, and I can't see the eyes, but anyhow, I suspect. I wanted to, it looks like I'm out of order, but I have to define this the set A prime. So I've got let's take a closed set in the dual group, and I'm going to call A prime of E the set of all pseudo-measures T where the support of T is contained in E. Why not? And then a theorem related to this full Nullstellensatz, where we look at the intersection of primary ideals and all that stuff and the algebraic geometers do. But let's just look at A and C. E is an S set if and only if A prime of E is equal to A prime S of E. And I'm defining A prime S of E to be the set of all elements supported by E such that for every K and for every psi in K of E, T of psi is equal to 0. So let's go over to the dual group here. I've got a pseudo measure T, and it's supported in this set here, E. And now I'm taking a function in K of E, so it's coming down right up to where the support of T is, and wherever the support of T is over here, and they kill each other. That's obvious with measures. That's an exercise in measure theory. But the fact that you have distributions more sophisticated than bounded Radon measures, where you have that annihilation, is the reason I define A prime of S. And so E is an S set if we have this annihilation property. And it's the first time you've seen it. I know these things. Sometimes they're complicated, but I'll be repetitive. That's the only thing I'll say about frames today. I'll be repetitive. So it's on the other hand, I am going to read this because this is a short, uninformative history. So Farmer Picasso had no finished no sooner finished his work on the farm building Pablo, or however you build a bull, I don't know. Whereas 3 years later, after leaving the Resistance and discovering distribution theory, Laurent Schwartz, a superstar, genuinely a superstar, proved that SD minus 1, the boundary of the closed unit ball in RD, when D is bigger than or equal to 0, is a non-S set, as opposed to that chintzy soccer ball, which is an S set. So this was really a victory for distribution theory. It was not too difficult. It's sort of a serious exercise in distribution theory, but it's not too difficult. But he couldn't get it. He couldn't find sets of non-synthesis in R or R2. And then along came, I couldn't think of a good name for Malevin. I call him a monarchist because he was. Now, I know we see some kings out there nowadays who are truly evil, despicable, selfish kings, but he wasn't. He was like he was like a, who, what's that? Not you, for Christ's sake. I'm going to say, no, you're the naive king, but you're not naive either. So, geez. Anyhow, monarchist Malevin, he proved that there exist non-S sets, non-sets of spectral synthesis in R and R2. So end of story if you just want to do that superficial stuff. If you want to get down and dirty, like that fantastic talk that Ursula gave yesterday, looking for different dimensions, definitions of dimension, and people did, because of this Fourier construction process of these two equivalent theories, one about ideals and one about Fourier reconstruction. I really want to read this third bullet. I call him Slick Nick. This is Nick Veropoulos. In those of you of a certain age, remember the fantastic things he did. He's probably still doing them. I lost track of them, although we were quite close early on. But he proved Malevin's theorem in the following way. I'd like to read all of this because it's fascinating to me. First of all, he began with Schwarz's counterexample, which is sort of easy. And it's a sphere. And he used topological tensor products. Now, why would he do that? Well, here it comes. Topological tensor products with a setting for Grothendieck's theory of nuclear spaces. You may know that. And nuclear spaces are themselves a consequence of Schwarz's topological tensor products because of their role in Schwarz's distribution theory. So this was high-falutin functional analysis, nuclear spaces and the like. Grothendieck sort of became famous, et cetera, et cetera. And not only is it because of his distribution theory, but because of Heaviside's operational calculus, which we're going to talk about in just a few minutes. I get to stop at 5, right? Okay, I can see now. Sorry about that. I'm talking too much. And machine learning is finite dimensional nuclear spaces. So there's no reason not to think as they build these huge data sensors, which are rotting the climates, or else we're going to build some up in space, bizarre idea, that we won't move to infinite dimensional nuclear spaces to do machine learning in AI. But that's just a thought. And then along came Killer Kerner. Kerner is a real man, but he's English. He's also a genius. And some of us have met him at Jim Ziltoko's. Anyhow, Kerner in 73 proved there exist Helson non-S sets in a complicated way, but he managed to do it in a mere 300 pages. So it was the proverbial death knell for spectral synthesis. we were all making a living. You're raising a family. You're able to bring home bread and stuff like that. And then Kerner comes along, and what the hell am I going to do now? So but it was like a pre-germination. I mean, things die, but sometimes I just want to talk about intellectual things. But sometimes they germinate in a way and arise in the present day, which is the part of my title about looking ahead. Okay. Now, in that paper of health that I mentioned, Helsensets, but that paper where I think this is the same paper, the reason you call them Collison frames, Helson uses that paper because those formulas, I haven't read Helson's paper for a while, are very reminiscent to me. But in any case, some of the main people of the day, I list them up there, but let me go to this step here. Malavans' proof required 3 parts. This proof of his theorem. Now, here Schwartz did something easy, and he gets the sphere in D bigger than equal 3. Malavans' proof required 3 parts. These are my words, but I may not be exaggerating enough. It's a sublime proof. I think it's labyrinthine in its technical work. He constructs a very complicated function, mu for Malavan. And then he developed a Heaviside type operational calculus. So he needed an operational calculus. And then he was able to combine them. But the construction of mu is really over the top. The operational calculus theorem is serious mathematics. Probably would have gotten him tenure at Harvard, but the function very few people could do, in my opinion. Okay, so this is a statement of the operational calculus, and I'm not going to read all of it, but I want to read in a very important condition in it, namely the first condition. So let's go down to the case where gamma is compact. For example, the circle group. And let's assume that there is a real valued function phi, an absolute convergent Fourier transform, Fourier series, actually, so that this inequality holds. And that takes the time to assimilate, and I've spent a lot of time in my life looking at that formula, but it's just harmonic analysis. Well, if you can find a function like that, then you fast forward through the theorem, hypotheses, and the proof, and you can show that if you define the zero set of phi to be E, then E is non-synthesis. So he had a way, not as elegant as Veropolis's, but with a lot of meat around the bone. In one of the things he had to do, I just want to mention this briefly, his function phi at this time of the day, you're not interested in all the details here, but had to satisfy an inequality, and it's this type of inequality. Okay. Now, and he proved it, and he became famous, and da-da-da-da-da. Sidebar, a number of years later, in fact, I was at Harvard with the guy, but I never met him, but he must have been extraordinarily smart, Ian Richards, and he died in his prime. That kills me to hear stories like that. But he proved the following theorem. He said, let's let gamma be compact. Then for every sigma bigger than 1, we can find a real valued function, rho, for Richards, sub sigma in A of gamma, and we can find a C, constant, depending on sigma bigger than 0, such that this A prime norm satisfies a big O relationship like this. And basically, that's the sort of thing we need to implement or to use the first inequality of that part of the Mallet-Van operational calculus. Well, but Richards did something completely different. He still needed the Mallet-Van operational calculus, but his function was simple by comparison to Mallet-Van's. And his function looked like this. It looks like this. Rho sigma of gamma is the sum from n equals 1 to infinity, 1 over n to the sigma, the real part of Rn, comma, gamma, where Rn is sequence in G, the group over here that I've been talking about. And it has to be suitably constructed. It's very combinatoric, fascinating to me. I love this sort of mathematics. Once he constructed that function, when I wrote the real part here, I'm just looking at if we take the circle group, gamma, and we take these integers, Rn, I'm just looking at e to the 2 pi I Rn gamma, and then looking at the real part of that. So just so there's no doubt. I think I'll skip this in light of the time. Anyhow, that rho, because of that inequality there, that rho sub sigma satisfies the hypothesis on phi in Mallet-Van's operational calculus. And so that means that this set E, zero set of rho phi, is non-S because for the same reason. I'm just implementing the operational calculus. Well, now I'm going to do something that seems really simple, but I get sort of more out of it than I should have. And let's take the circle group, and let me just stop saying gamma. Let's look at this Dirichlet series. So I'm now taking rho of S to be the sum from n equals 1 to infinity, 1 over n to the S, e to the I Rn gamma. But now I'm letting S be a complex number, sigma plus I tau. Now, you notice immediately that it's not really just rho of S. It's rho depends on S, that complex number. So we're in a half plane here. And R of n is going to be an integer, and gamma is going to be in my group. And so that's, for those of you who know what a Dirichlet is, that's a Dirichlet series. And if the first time you ever saw one, that's a Dirichlet series. So, and they have their Laplace-Dietrich transforms defined by discrete measures, and they have abscisses of absolute convergence. Our boy Harold Bohr was a superstar in them. And I'm going to skip this last bullet because I'm going to say more about it in just a minute. But anyhow, once I saw this, which was a trivial observation, I realized there were things that I should do. And so if we take the circle group and we fix a sequence, essentially just looking Rn equal e to the n, just for the positive integers, and consider this function rho that I just defined, which actually depends not only on S, but on R and gamma, then, lo and behold, for every S in C on the right half plane of convergence of the Dirichlet series, I can find a constant m sub sigma, and I can find a delta sub sigma bigger than 0. So I'm just looking at the real part now, not at the rest of the plane. I've got a Dirichlet series. Here's 1, and the darn thing converges. Well, you're looking at it this way. 1, and the thing converges all the way over here. Not just on the line. I don't have to worry about the line. I got the whole plane. And lo and behold, I can, because of this flexibility I have in the coefficients, I can, for lots of different sequences, I can get this inequality. And in particular, I can get the Mallet-Van operational calculus to work. And so what I have is that the zero set of the real part of rho SR and that's the gamma in the compact group, is non-S. So now I've got a gazillion non-S sets. Now, you may not want non-S sets in the world, but I got a gazillion of them here. So, and that also means we can redraw lots of the complex plane to get different regions of synthesis and non-synthesis. And it also means we have great flexibility in the RNs. For example, what sort of surprised me was, I stumbled on it. Just like I stumbled on Chris, you say, geez, what the heck? But anyhow, what sort of surprised me, I needed lacunarity, but if I let it be too lacunary, it didn't work. I just had to have a balance between lacunarity and non-lacunarity. So there's stuff going on here, which is very interesting to me. And I'm in the middle of this now, in the sense that I've got results like this, but there's, if you want really, and people I don't think necessarily want this, but if you want really technical results that give you specific answers about synthesis, this is a vehicle to do it with. So that's one of the looking ahead problems. Very conventional, but technical, I would say. And it really does go back to Richards, and just a trivial observation on my part. Now, another very basic problem, which I don't think people are going to work on, just because it's not sexy nowadays, but a basic, seemingly little big problem is the question, is the union of two sets of spectral synthesis a set of spectral synthesis? Oh my God, can you have a theory when the union of two of them is not? Well, yeah, but you really want to answer this question. And lots of special cases are known. I'm definitely not advertising my book, but I was sort of like a little secretary. I kept track of everything that was known. The world experts right now, and I'm sure Eve is not working on them, but Eve Mayer is certainly one of them. But two of my best friends, and Eve's a friend too, but Ray Johnson and Bob Warner. And I just wanted to mention their work, the work of Eve, you probably know. And now I want to close with two problems which I think, to me, are exciting, one of which I will never be able to do anything about because I really don't understand geometry. So this is one of them. And Ingve Domar is the driving force here. Basically, to develop the theory of spectral synthesis of Euclidean geometric structures. I mean, he made a foray into this field in the early 70s. Sadly, he passed away in 2014, where curvature, the type of manifold, plays a role. I personally think this is of great interest nowadays for dimension reduction. I mean, the types of problems that Masson was talking about today are not unrelated to me. The clustering problems, those are problems where you really need to look at curves, how things are placed in space. And synthesis has lots of power. I mean, the techniques that have been developed are really amazing. And I think this is one of the places, someone who really understood geometry, understood the applicability of clustering and dimension reduction. I think this is an important field. My last slide, and this I really do want to read because this does interest me, and I still can't see the eyes back there. So we can formulate Wiener's and Berling's theory of spectral synthesis of Banach algebras. I just did it for L1, but in fact, a lot of us have done it for topological algebras of various stripes. But we can formulate Wiener's and Berling's theory of spectral synthesis of Banach algebras in terms of a wavelet approximation theory where the approximants of a function are required to be supported within the support of the function. I want us all to understand this a little bit because I think it's quite interesting, and it's not the way we did it in terms of the support, where those are like exponentials and you're making a Fourier expansion. And there are real applications for the subject. So I said that, if it's percolating or it's not with you. But let's go to the second bullet. Well, it percolates or doesn't. This is not the case for L2 wavelet theory. Basically, when you do an L2 wavelet, you cannot have the wavelet expansion that you want for an orthonormal basis, for example, or a wavelet frame in the support of the tumor you might be analyzing in a medical situation. It spreads out. Now, when can you, though? Well, you can some of the time. And so I just want to address this third bullet. Years ago, in the 80s, I did some silly calculations where I proved stuff like I just said, but I never wrote it up. And then one of my students came along, Junjie, and he really was an expert with computers, and that's just what I needed. And so for higher wavelets, we've proved with Junjie in a constructive, computable way that such approximation can be effected for LP spaces between 0 and 1. Now, that's fascinating nowadays because of the role of sparsity and compressed sensing. I can't get it so that I have an L2 theory, which I denigrated already by calling it deodorized, but it's relevant because I can hopefully use it in the context of sparsity and compressed sensing for this, because in that case, if I take a tumor, or a medical doctor takes a tumor, and wants to do an analysis to find cancer in that tumor, and wants to use a wavelet analysis, I just did it with higher wavelets, but then you can. And so I want to just close by saying there are genuine applications, and the one I know best is the external beam radiation therapy, but there are lots of other applications where you really want to do approximation from within, which I now call internal synthesis. And I know I haven't said anything about frames, and I know it's okay to be repetitive if you're a frame expert, so I am going to be repetitive. Happy birthday again, Chris.